All right. Hello, guys, and welcome back to another kind of walkthrough of a chapter of Introduction to Solid-State Physics. Today, we're going to be going over Chapter 2, which is going to detail wave diffraction and the reciprocal lattice. We're going to start off with Bragg's law, then getting into kind of scattered wave amplitudes with some Fourier analysis, see how that ties into reciprocal lattice vectors, then get into the conditions needed for diffraction, and then the Laue equations. Then we'll talk about Brillouin zones, and then we're going to do a Fourier analysis of the basis. So let's get started with Bragg's law. So we study crystal structure through the diffraction of photons, neutrons, electrons. Figure 1, if you go to figure 1, over here we can see the wavelength versus particle energy for photons, neutrons, and electrons. So we can kind of use how they bounce off of stuff to kind of recreate the crystal structure. So the diffraction depends on the crystal structure and on the wavelength. So at optical wavelengths, around 5,000 angstroms, the superposition of the waves scatter elastically by the individual atoms of a crystal result in ordinary optical refraction. And it's not as useful for basically getting the crystal structure or something. When the wavelength of the radiation, though, is comparable with or smaller than the lattice constant, if you remember, one second, let me change my thing. My computer crashed last time I started recording, so hopefully this works now. All right, it works, perfect. Okay, so when the wavelength of the radiation is comparable to the lattice constant, if you guys remember, is A, given by basically how big each unit cell is, basically. A-dimensional unit cell is. It's on the order of angstroms, basically. So 5,000 angstroms, right? Much too high. But if we get a wavelength, say around 1.5 angstroms, it's a very common wavelength used for X-ray photons, for XRD. What we find then is that it's much more useful. So we find diffracted beams in directions quite different from the incident direction. So instead of getting high wavelength, right, it just bounces back. But if it's on the same order, then it can bounce like that, and we'll see what that does. So Bragg basically had a very cute derivation that said, suppose the incident waves are reflected speculatively from parallel planes of atoms in the crystal, with each plane reflecting only a very small fraction of the radiation, like a lightly silvered mirror. So we have a bunch of atoms like this, right? So forth, and then you can imagine it extends to infinity downwards and other ways. Each kind of layer of atoms is like a mirror, right? But stuff can still pass through it. What we can do then is we'll say the parallel lattice planes are spaced d apart, okay? And we want to measure the path difference of, say, the top path, this one, to this one. And it turns out, with a little bit of geometry, we get the path difference is 2d sine theta. And we can see that if I were to show you from this diagram here, or I could just draw it, I guess. But honestly, their diagram is better, so I'm just going to talk about it. So we have an angle theta coming in, right? And since these two things are parallel, this angle right here is also theta, etc. And then we can get this angle right here is also theta. So then the path length difference, right, is this path length is the same as this path length right here. And then we get this little red part, boop, boop. And then we get the green part. And we see that this one of the red lengths is d sine theta, and there's two of them. So we get path length of 2d sine theta, right? So that then lets us write that constructive interference of the radiation from successive planes, right, are going to happen when 2d sine theta is equal to n lambda, where n is some integer. And Bragg's law can only be satisfied for wavelengths where lambda is less than or equal to 2d, right? Since we'll say n equals 1 to make it the lowest possible. So then we get sine theta equals lambda over 2d, right? And then this has to be less than or equal to 1. So lambda has to be less than or equal to 2d. Perfect. Okay, so although reflection from each plane is specular, for only certain values of theta will reflections from all periodic parallel planes add up in phase to give a strong reflected beam. So basically, if each plane are perfectly reflecting, only the first plane of parallel set would see the radiation, and any wavelength would be reflected. But each plane only reflects about 10 to the negative 3 or to the negative 5 of the incident radiation, so that 10 to the 3, 10 to the 5 planes may contribute to the formation of Bragg reflected beams in a perfect crystal. What that's saying is, if it was like a perfect mirror, only the top layer would show, right? But since like it's rare that it happens, basically, you can get up to 10 to the 5 layers contributing to this. Okay. And Bragg's law is a consequence of the periodicity of the lattice. And notice that the law does not refer to the composition of the basis of atoms associated. In other words, it doesn't matter if it's like, like copper or carbon, whatever. It's based off of the lattice structure, aka how they're arranged in space. Okay. So, however, we're going to see that the composition of the basis determines the relative intensity of the various orders of diffraction, denoted by n above, for a given set of parallel planes. So, basically, composition will matter slightly in terms of how much is let through. If you're at 10 to the 3 or 10 to the 5, like layers contributing. So, if we can look at one of these, this is a good example. Figure 3, monochromator. Okay. And you see they use a 1.16 angstrom beam. I think in my lab we used 1.49, something like that. Regardless, and you get kind of intensity peaks here where you see that you get the condition of 2D sine theta, basically. Okay. And here are them repeated peaks for powdered silicon. Okay. So now we can talk about how so the Bragg derivation of the diffraction condition gave a neat statement on the condition of the constructive interference of waves, right? But we need kind of a deeper analysis. That was just kind of a geometric one to determine the scattering intensity from the basis of atoms, which means from the spatial distribution of the electrons within each cell. So this is where your knowledge from earlier classes are going to help, because we're going to be doing some Fourier analysis. Fourier, I don't know. So basically, right, crystal, right, is just a periodic arrangement of atoms. So that means they're going to be invariant under translation of any form T, where T is U1, A1, plus U2, A2, plus U3, A3, where A1, A2, A3 are the lattice vectors. Or I guess crystal axes, same thing. And then, right, if I have a crystal like this, and I move over by like 0, 1, 1, whatever, and then I go to the same crystal, it looks the same because it's basically an infinite, we're treating the crystal as an infinite amount of atoms, basically. So the point is that none of the properties should change if you move along the crystal axes by integer multiples. So that should mean then that the charge concentration, electron number density, magnetic moment density, all that is invariant under T. So if we look at the most important one, which is the electron number density, which we can denote by n of r, right? We could say it's a periodic function of r with periods A1, A2, and A3 in the direction of A1, A2, A3. In other words, n of r is equal to n of r plus t. So adding it shouldn't matter. Like if you're at this atom right here, you should get the same electron density than if you move to this atom over here. Okay. So this periodicity, right, means it's kind of perfect for Fourier analysis. So the most interesting properties of crystals are directly related to the Fourier components of the electron density. So first, let's consider in one dimension the function n of x, right? And we can expand into a Fourier series of sines and cosines. So, and not whatever you start off with, plus, and then it's just your sum of cosines and sines. Cp cosine 2 pi p x over a plus sp 2 pi. You might have seen in your classes this done with exponentials. We'll see that later because it's much neater. But basically here, p are positive integers, and we have Cp and Sp as real constants that are the Fourier coefficients of the expansion. And then we have this 2 pi over a, which ensures the periodicity of, has a period of a. N of x is a period of a, which is what we want from the crystal, right? In other words, such that if I add a to my position, I should get the same answer, right? So n naught plus this whole thing again. So you'd be cosine 2 pi px over a plus 2 pi p, right? Because I just added nx plus a. So you see the a cancels out. Plus sp, and then we have 2 pi px over a plus 2 pi p, right? And if I have a sine or cosine wave, right, and let's say I have this point right here, and I add 2 pi, well, I'm just going to go over here, right? And that's the same value, right? And this p is just a positive integer, right? Which means I'm adding 2 pi, 4 pi, 5 pi, 6 pi, sorry, 2 pi, 4 pi, 6 pi, 8 pi, etc. So you're always adding multiples of that, so you're always getting the same answer, so these don't even matter. They just go away. It's just a useless phase, basically. It doesn't change the phase. So we basically get the exact same thing of this answer right here. Okay. Then we can say that 2 pi p over a is a point in the reciprocal lattice or Fourier space of the crystal. So in one dimension, right, these points lie in a line, and the reciprocal lattice points tell us the allowed terms in the Fourier series. This is the Fourier series right here. Or I guess this one up here is probably better because it's without the useless phase. And a term is allowed if it is consistent with the periodicity of the crystal, as in figure 5. In other words, a periodic function n of x of period a in the terms 2 pi over a that may appear in the Fourier transform, and here they're using the exponential form. And we see what's allowed and what's not. So in the exponential form, right, remember we can use Euler's decomposition, and we can say sum over p, we have n of p, e to the I 2 pi px over a, right? Because we can break our cosine and sines into an exponential. And this sum is over all integers p. So p is no longer just greater than 0. It's positive, negative, and 0. And now these n sub p, that should be a subscript. Make sure it doesn't text me. All right, we're good. Such that the conjugate, complex conjugate, of negative p has to equal the positive value of p for the sum of the terms of p and negative p to be real. So we can say, let's say phi is equal to 2 pi x, 2 pi px over a. Sorry. Then we can rewrite the sum as np cosine phi plus I sine phi plus n negative p cosine of phi minus I sine phi, right? From the condition that we want the sum of the terms in p and negative p to be real, such that n conjugate negative p is equal to n of p. Then we get np plus n negative p cosine phi plus I np minus n negative p sine phi, which is equal to 2, right? Because we have np plus negative p, which are the same, 2 real of np cosine phi plus, plus 2 imaginary, minus 2, sorry, I messed up, minus 2 imaginary of np, like the imaginary part, sine phi, where this and this are both real numbers and denote the real and imaginary parts of np. So therefore, the number density n of x that we want is a real function, which should be a real function, right? Because that's what we're measuring and we see it. So what we can do then is extend this one-dimensional case to a three-dimensional case, which is going to look very familiar if you ever studied waves or stuff like that. So we can say the periodic value of n now of r is the sum over g of ng e to the I g dot r. Now tell me that does not look e to the I kr. It looks very similar to your waves, your plane waves, stuff like that. And what we have see then, we need to find a set of vectors g such that this is invariant, so n of r is invariant under all crystal translations of t that leave the crystal invariant. So it will be shown that the set of Fourier coefficients n of g determines the X-ray scattering amplitudes. That's how we get the scattering amplitudes. So now what we need to do is an inversion of the Fourier series. So inversion of Fourier series. Okay, so we want to show that the Fourier coefficient NP in the series 5, which is this one right here, is given by this. So N of P is equal to A inverse. I'm going to write it as 1 over A. It looks better. Integral 0 to A dx N of X. This is quite literally just how you do a Fourier, well, I guess inverse Fourier too, series. Px over A. Okay, because we just took the sum and turned it into an integral. Okay, so we want to substitute 5. So 5 is this equation right here. Let me turn on the draw. Into 10 for N of X. Okay, so then what we get then is we get 1 over A, this sum over here over P prime of NP prime, integral 0 A dx e to the I 2 pi P prime minus P, okay, because we had a P here, we had a P prime coming in from there, X over A. Okay, and what this then tells us, if P prime does not equal P, so this sum right here, because this sum P prime is over all these values, you know, like let's say P is 5, it's 0, 1, 2, 3, 4, 5, 6, 7, 8. So if P prime does not equal P, so let's say for example we have 6 minus 5, that's going to give me a non-zero in the exponent, right? Then we get the value of the integral then is going to be A over I 2 pi P prime minus P. This is non-zero. E to the I 2 pi P prime minus P minus 1. Which has to be 0 because we're getting a value of e to the I 2 pi or 4 pi or 6 pi or 8 pi. Anything like that is always going to give you a 1 for this value right here, and we have e, that minus 1 is 0. So then we basically require P prime to be P, so we get rid of the infinite sum over here. So then that tells us that P prime has to be P, and then as for in 10, this expression right here, we can basically give the inversion of 9. So the inversion of 9 was our kind of more complicated three-dimensional version of 5. Equation 5 was the NPs. So then we can say that N of G, the coefficient G, is instead of 1 over A, now we have 1 over the volume of the cell over integral of the cell dv. So we have like a spatial integral now that's in 3 dimensions, which should make sense because we're doing it in 3 dimensions. N of R e to the I negative ig dot R, right? And this basically looks identical to this expression over here. And then if we plug in N of R instead of N of X. Okay, so if we want to get to the reciprocal lattice vectors now with from the Fourier analysis, let me write reciprocal lattice vectors. We have to find the vectors G of the Fourier sum and G e to the I G dot R, aka equation 9. And there's a kind of powerful, somewhat abstract procedure for doing this. And this procedure forms a theoretical basis for much of solid-state physics, where Fourier analysis is basically your bread and butter. So let's construct some axis vectors of the reciprocal lattice. So for the normal lattice, right, we have vectors A1, A2, A3. Since we're physicists, not very creative, we're going to call the reciprocal lattice B1, B2, B3. So we can say B1 equals 2 pi, these are vectors by the way, A2 cross A3 over A1 dotted A2 cross A3. Now, think for a second what the bottom is. A1 cross A2 cross A3. That is just the volume of the cubic cell. So remember that. And then I guess I won't write the rest. I'll just screenshot them. And normally in crystallography, we don't really use the factor of 2 pi. But for solid state physics, it's convenient because we can see where it comes from. So if A1, A2, and A3 are the primitive vectors of the crystal lattice, then B1, B2, and B3 are the primitive vectors of the reciprocal lattice. So each vector defined by 13, this equation here, is orthogonal to 2 axis vectors of the crystal lattice. Thus, B1, B2, and B3 have the property such that Bi dot Aj is equal to 2 pi delta Ij. So so basically if I dot B1 with A1, I get something. I get 2 pi. If I dot B1 with A2, I get 0. If I dot B1 with A3, I get 0, and so forth. If you guys remember how the Kronecker delta works, it's delta Ij equals 1 if I equals J, else 0. Okay, so we can say points in the reciprocal lattice are mapped by a set of vectors, G, such that we have, I don't know if that's new or V, I'm just going to call it V, it's probably new though, I'm sorry, B1 plus V2, B2 plus V3, B3. I can never draw new anyways, it looks the same. Where it should look very similar to our normal lattice vectors, right? It's just we're using the reciprocal ones and they have different coefficients as well. So a vector G of this form is a reciprocal lattice vector. So the vectors G in the Fourier series are just the reciprocal lattice vectors. So for them, the Fourier series representation of the electron density has the desired invariance under any crystal translation of, T equals U1, A1 plus U2, A2 plus U3, A3. So then we can write, okay, so that means if I translate this by that translation vector, we should, it should be invariant, right? So I could say n of r plus t is equal to sum over g and g e to the I g dot r e to the I g dot t from our law of exponents, right? Okay. However, this e to the g dot t, I'm going to now show equals 1. And then clearly it's invariant, right? Because this is just the expression for n of r. That's because e to the I g dot t is equal to e to the I v1, b1 plus v2, b2 plus v3, b3 dotted with u1, a1 plus u2, a2 plus u3, a3. And we just saw if I dot b1 with a1, we're chilling, that's something. If I dot b1 with a2 or b1 with a3, that's 0. So that then tells us then that this right here is just equal to e to the I 2 pi, because we have that factor of 2 pi, if you remember, from over here. V1 u1 plus v2 u2 plus v3 u3. Right? Since v1 b1 times u1 a1 stays, and then v1 b1 u2 a2 does not stay, because we need basically the indices to be the same. And what happens then, we have, since we know that this expression right here of v1 u1, so v1 is an integer, u1 is an integer, so an integer times an integer is always an integer, is integer. So I have one integer, let me highlight, one integer here, 2 integers multiplied together, which is still an integer, plus 2 more integers multiplied together, plus 2 more integers multiplied together, which is always an integer, right? So I have e to the I 2 pi, right? I 2 pi times some wacky integer, right? Therefore, this is just 1, right? So therefore, we can just cross that off and we can say n of r plus t equals n of r, which is just over g, n of g e to the I g dot r. See that? So therefore, every crystal structure has two lattices associated with it, the crystal lattice and the reciprocal lattice. And the diffraction pattern of a crystal, which is what we're going to find out, is a map of the reciprocal lattice of the crystal, which then, right, we can just inverse Fourier transform and we get the actual lattice of the crystal. So a microscope image, if it could be resolved on enough fine scale, is a map of the crystal structure in real space. So the two lattices are related by the definition in 13, which is the B1 equals 2 pi A2 cross A3 over A1 dot A2 cross A3. This is just volume of the cubic cell, but same thing. Okay. So then, and actually I'm pretty sure we can use microscopes nowadays to like physically see the crystal structure of certain stuff if we use an electron microscope. But anyways, so yeah, okay. So when we rotate a crystal in a holder, we rotate both the direct lattice and the reciprocal lattice, which should make sense, right? Because you'll get a different pattern for the reciprocal lattice on your diffraction, so your normal lattice should also have a different pattern, meaning it's rotated. So vectors in the direct lattice have the dimensions of length, right? And vectors in the reciprocal lattice, it's reciprocal, have dimensions of 1 over length. So the reciprocal lattice is a lattice in Fourier space associated with the crystal. And the term is motivated below. So wave vectors are always drawn in Fourier space so that every position in Fourier space may have a meaning as a description of a wave. But there is a special significance to the points defined by the set of G associated with the crystal structure. So let's look at a theorem for diffraction conditions. So the set of reciprocal lattice vectors G determines the possible X-ray reflections, which means that if we don't have a reciprocal lattice vector at a certain point, we should not see an X-ray reflection there. So we see in figure 6, this is figure 6, that the difference in phase factors is e to the I k minus k prime dot r. So here I have k, here I have k prime, and if I subtract the two, right, I get the difference. Scatter volumes are apart. So the wave vectors of the incoming and outgoing beams are k and k prime. So let's see. Yeah. Okay, so let's suppose that the amplitude of the wave scattered from a volume element is proportional to the local electron concentration n of r. So then the total amplitude of the scattered wave in the dimension k prime is proportional to the integral over to the crystal n of r dv times the phase factor exponential. So we can say then that the scattering amplitude f is the integral dv of n of r e to the I minus the difference of the phase factor k minus k prime dot r, which is just the integral dv n of r e to the I negative, delta k dot r. Delta k, as seen in figure 7, right, is just the difference between the two. So k plus delta k, it gives me k prime. So it's just, that's one way to define it. Okay, so then we can say, I guess k plus delta k equals k prime, where delta k measures the change in wave vector and is called the scattering wave vector, right? Because k was then changed by delta k and got k prime. Okay. So we can introduce into equation 18, this is equation 18, the Fourier components of n of r from equation 9 to get the scattering amplitude. So we have f equals, okay, sum over g now, integral dv n of g e to the I g minus delta k dot r. Okay. When the scattering vector delta k is equal to a reciprocal lattice vector, so when delta k equals g, right, the argument of the exponential vanishes, and f is then equal to just v and then ng, right, the volume, because then we get these two are equal, right? So we have 0 there, so we have e to the 0 is just 1, so we have integral of dv times ng, which is just v times ng. So we can do a simple exercise later, I guess, on your own, to show that f is negligibly small when delta k differs significantly from any reciprocal lattice vector. In other words, it's a fancy way of saying if delta k is, so if these two people don't equal each other and they're different, then f is going to be super small and the scattering amplitude is very small, so we won't actually see something in our X-ray diffraction. So in this elastic scattering of a photon, its energy, right, h bar omega, is conserved such that the frequency omega prime equals c k prime of the emergent beam is equal to the frequency of the incident beam. So therefore, the magnitudes of k is equal to the magnitude of k prime, such that k squared is equal to k prime squared, which is what I just wrote there. Whatever. So basically then, since we know this expression here, we can then say then that delta k equals g, or k plus g equals k prime. So therefore, the diffraction condition is k plus g, both vectors, squared equals k squared, or 2k dot g plus g squared equals 0. So this is the central result of the theory of elastic scattering of waves in a periodic lattice. So g is a reciprocal lattice vector, so is negative g. So with this substitution, we can write this one as 2k dot g equals g squared. Since if g is a lattice vector, so too is negative g, right? Because it's a translation property. Okay. My little cousin texted me, so I will stop recording. Actually, wait, let me see. Problem 1. Give me 1 second. Yeah. All right. Stop. All right. I'm back, guys. Sorry about the interruption. My internet went out. But as we were just talking about, G is also a reciprocal lattice vector. So this equation 23, oops, different color, is another statement of the Bragg condition. So the result of problem 1, some problem we haven't done yet, but basically is the spacing between parallel lattice planes that are normal to the direction G equals HB1 plus KB2 plus LB3 is 2 pi over magnitude of G. So therefore, we can write this expression as 2 pi over lambda sine theta is equal to 2 pi over d HKL, which looks like 2d sine theta equals, I guess it's the flipped version of that, but yeah. Okay, so this then tells us then that 2d HKL sine theta equals lambda, which is Bragg's law, right? Where theta is the angle between the incident beam and the crystal plane. So the HKL integers that define G are not necessarily identical to the indices of the actual crystal plane, where, you know, we have like N1, N2, N3, or whatever you want to use. But okay, so thus we obtain the Bragg result again, where 2d sine theta equals n lambda, where d is the spacing between the planes, if you guys remember, diffraction like that. So this right here is d, the interplanar spacing. Lambda is the wavelength of the incident light, usually on the order of an angstrom. And then the d is the spacing between adjacent parallel planes with indices of h over n, k over n, l over n. Okay, so now let's get into the Laue equations. Okay, so the original result of the diffraction theory, basically that delta k is equal to g, can be expressed another way, which is what are called the Laue equations. So these are valuable because they're geometric representation. So let's take the scalar product of both delta k and g successively with a1, a2, and a3, and then we get a1 dot delta k equals 2 pi v1, a2, these are all vectors. I should be drawing the vector arrows over them, but I'm lazy. Dot delta k equals 2 pi v2, and then a3 dot delta k equals 2 pi v3, where we immediately see, right, that the delta k vector is the direction of g, so a1 and the first component v1 of G. So L is going to point in the A1 direction. Same with A2 goes the second component of G, and A3 goes the third component of G. So these equations have a very simple geometric interpretation. The first equation, right, A1 dot delta K equals 2 pi V1, tells us that delta K lies on a certain cone about the direction of A1. Direction of A1, and we have a little cone. Bad drawing, but I think they have a photo later on. Oh, why is my eraser not working? There we go. Okay, and then same with the other two. So we basically have 3 cones, right? So thus, at a reflection delta K, they have to satisfy these 3 equations. So we have these 3 cones, and they all intersect. So let's see. So yeah, it must lie in a common line of intersection of the 3 cones, which is a severe condition that can only be satisfied by a systematic sweeping or searching in wavelength or crystal orientation, or by sheer accident. So that's why when you do XRD, what you do is you actually sweep an angle of theta, or 2 theta. So you sweep a bunch of angles for your X-ray comes in at like this angle, this angle, this angle, this angle, and so forth. Okay. So a beautiful construction, the Ewald construction, is exhibited in figure 8, which kind of helps us visualize the nature of the accident that must occur in order to satisfy the diffraction condition in 3 dimensions. So let's look at this for a second. Here we go. See if you can understand this diagram. So here's our delta K vector, or G vector, right? And the points on the right-hand side are reciprocal lattice points of crystal. These are the reciprocal lattice points. So the vector K is drawn from the direction of the incident X-ray beam. So our X-ray beam goes like this, okay? And then we draw a radius of a sphere of radius K equals 2 pi over lambda about the origin of K. So we start here and draw our little circle right here. If I could draw that, you'd understand better, but it's the white circle. And a diffracted beam will form if the sphere intersects any other point in the reciprocal lattice. And we see that it happens right here, intersects it. So then we get the K prime vector like that. And we see that diffraction is going to happen when K prime equals K plus G. So it's going to diffract at that point. All right. Now let's talk about Brillouin zones. Okay. So Brillouin, I'm probably pronouncing that wrong, but gave the statement of the diffraction condition that is most widely used in solid-state physics, which means in the description of electron energy band theory and the elementary excitations of other kinds. So a Brillouin zone is defined as a Wigner-Seitz primitive cell in the reciprocal lattice. So if you guys remember what the Wigner-Seitz is, if I have, I don't know, here's my lattice, here's a hexagonal lattice, right? I draw, this is in 2 dimensions. I want to draw the Wigner-Seitz. I look at the midpoint of each one, draw orthogonal, 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 orthogonal. And for the hexagonal, it's just another hexagonal cell that's rotated 30 degrees with respect to the original. Okay, so the Brillouin zone gives a vivid geometrical interpretation of the diffraction condition, which is 2k dot g equals g squared. So we divide both sides by 4 to obtain k times 1/2 g equals 1/2 g squared. Okay. Probably by equation 4 is what they meant, not by 4. So we'll now work in the reciprocal space, the space of k's and g's. So let's select a vector g from the origin to a reciprocal lattice point. Okay. So construct a plane normal to this vector g at its midpoint. So this plane forms a part of the zone boundary. So all we're doing here is instead of working in the normal lattice space, we're working in the reciprocal lattice. And we're just making a, let's say a reciprocal lattice look like this. Let's say we have a square lattice, okay, in real space. We're going to do this in 2Ds. So we have a square lattice. Okay, well, luckily, in reciprocal space, it looks the same thing. Okay, it's just the lengths are stretched by 2 pi, or divided by 2 pi. So it looks identical, and we're just working in this space right here. So let's say, for example, I want to choose this point right here. What I'm going to do then is I'm going to draw a line to all the nearest neighbors. Technically, I could draw to here too, but you'll see why it won't matter if I could draw my diagram correctly. and I look at the midpoint of each one, right there, right there, right there, and right there. So it turns out, since he's at the cusp, these don't even matter, but that's what the Brillouin zone would be for the reciprocal space of a two-dimensional Keepic lattice. Okay. But anyways, so this plane that we're forming, so we want to construct a plane normal to this vector g at its midpoint. Well, we're in 2 dimensions, so we can't do that, but in 3 dimensions, you'd construct a plane. And that forms part of a zone boundary. So an X-ray beam in the crystal will be diffracted if its wave vector k has the magnitude and direction required by this equation here, 26. And the diffracted beam will then be in the direction of k minus g, aka k prime, as we saw from equation 19, where k plus k prime equals delta k, I think, right? Something along that. Might be missing a plus sign. So therefore, we get delta k equals negative g. Because remember, if g is a reciprocal lattice vector, so too is negative g. So thus, the Brillouin construction exhibits all the wave vectors k, which can be Bragg reflected by the crystal. So let's try to look at this in a nice reciprocal lattice. So in figure 9a, I guess I can just draw on this one here. So reciprocal lattice points near the point O at the origin of the reciprocal lattice. So the reciprocal lattice vector GC connects the point OC over here. GD connects OD, O to D. Okay, and then 2 planes, 1 and 2 are drawn, which are the perpendicular bisectors of GC and GD. So you see they found the midpoint of the 2, and they went boop, and then they went boop. Okay. Let me erase all these diagrams. You guys can see that, because the white ones are what they're talking about. So any vector from the origin to the plane 1, such as k1, will satisfy the diffraction condition, because k1 dot 1/2 GC, so k1 dotted with GC, okay, equals 1/2 GC squared. Any vector from the origin, from O, to plane 2, so this vector, this vector, this vector, any of these vectors basically, is going to satisfy the diffraction condition, such as k2 dot 1/2 GD equals 1/2 GD squared. So here's an example of the square reciprocal lattice with reciprocal lattice vectors shown as fine black lines. So they started with the square lattice, and you guys can kind of see in the reciprocal space it's still a square lattice. The square is the Wigner-Seitz permanent cell of the reciprocal lattice. Right here, you guys can see it. Okay, kind of what I tried to draw earlier. And it's called the first Brillouin zone. So we can see that if we take the white lines, right, are the normals. So we have the normal 1 here, normal 2, normal 3, normal 4. So a vector I could draw like from the origin like that, that's a valid 1, that's a valid 1, that's a valid wave vector, that's a valid wave vector, and so forth. Okay. Okay, so then the set of planes that are perpendicular bisectors of the reciprocal lattice vectors is of general importance to the theory of wave propagation in crystals. So a wave whose wave vector drawn from the origin terminates on any of these planes are going to satisfy the condition for diffraction. That's what we were talking about right here, where like if I draw this wave vector like that, that's a valid wave vector. K is Gucci. Good. Okay. So these planes divide the Fourier space of the crystal into fragments, as shown in figure 9b for a square lattice, right? We have these fragments here, 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 here. Only those allowed spaces are allowed. The central square is a primitive cell of the reciprocal lattice. It's the Wigner-Seitz cell of the reciprocal lattice. That's what I showed here. Okay, so the central cell in the reciprocal lattice is of special importance, and we call it the first Brillouin zone, where the first Brillouin zone is the smallest volume entirely enclosed by planes that are perpendicular bisectors of the reciprocal lattice vectors drawn from the origin. In other words, it's when you're trying to make the Wigner-Seitz cell, basically. Examples are shown in figure 10 and figure 11. Okay, we'll look at those in a second. Actually, we can just look now. So figure 10, here's a more fancier looking cell. It's no longer square, but you see we get this right here is the first Brillouin zone right here, right? And that's just the Wigner-Seitz cell. Okay. And I guess for the linear case, here it is again. It's just, I guess it's It's infinite up, but whatever. Okay, so let's say we want to go reciprocal lattice to simple cubic lattice. Reciprocal, this is a simple case because they're very similar lattices, to simple cubic lattice. So the primitive translation vectors of a simple cubic lattice are taken as a1 equals a x hat, a2 equals a y hat, a3 equals a z hat, right? It's just, right, nice simple cubic where we have a1, a2, a3. Okay, so what we can do then is, if we follow the standard procedure, equation 13, which is, if I remember correctly, I might be wrong, b1 equals a2 cross a3 over volume cubic. I'm missing something here, aren't I? Equation 13. There's a 2 pi. There's a 2 pi on top, I'm pretty sure. Yeah, here it is. Here it is. Oh, I had it right. Let's go. Okay. B1, I just forgot 2 pi. Yeah, okay, nice. So that's the expression. If we follow that for the simple cubic case, which I can do an example. So for simple cubic, right, a2 cross a3. So a2 cross a3, that just gives us a1. So then b1 equals 2 pi a1 over vc, where volume of the simple cubic, right, is a cubed, as you can see right here. So we get the primitive lattice vectors of b1 equals 2 pi over a x hat, b2 equals 2 pi over a y hat, and b3 equals 2 pi over a z hat. So why do I have an a cube, though, is the question. Interesting. Okay. I guess the a1, so it should cancel out. Okay. Anyways, so what we basically did is we just made another simple cubic lattice, except our a went to a prime, which is equal to 2 pi over a. Hence the name reciprocal, right? Because it's 1 over. But okay, so the boundaries of the first Brillouin zones are the planes normal to the 6 reciprocal lattice vectors, plus or minus b1, plus or minus b2, plus or minus b3 at their midpoints. So the 6 planes bound a cube of edge 2 pi over a and a volume of 2 pi over a cubed. This cube is the first Brillouin zone of the simple cubic lattice. So primitive 12, this is for the BCC, and this is for, okay, and then this is for the first Brillouin zone of the BCC. Okay, nice. So I guess we'll see this in figure 12. So that was for the simple cubic case, very simple, right? However, BCC and FCC are more complicated. So let's see. Reciprocal lattice to BCC lattice. This is where you might actually take the dot products. So if we want the primitive translation vectors, right, A1 is equal to 1/2, I guess I'll write it their way, A negative x hat plus y hat plus z hat. I'll normally write this as like A2, I'll show you right here, equals 1/2 A, and then I'll do 1 negative 1 1. I'll just know what they mean. X hat, y hat, z hat. And then we have A3 equals 1/2 1 1 negative 1, which we can immediately see here, right? So if you look here for A1 right here, A1 is, minus in the x direction 1. So minus x direction 1 is this way. Okay, and then we go, we go in 1/2, right? So the factor 1/2. Then we go plus y hat. So plus y hat 1/2, like that. And then we go plus 1/2 of z hat up there, and we hit the thing. And we can do that for all 3. Boop, boop, boop. And then boop, boop, boop. That was a terrible drawing. Boop, boop, boop. There you go. That's what I meant to do. Okay. So we get these vectors, and then we want to find the volume, right? So the volume is given by A1 dot A2 cross A3, which is equal to 1/2 A cubed, which we should know, right? Because in a BCC cell, in the whole cube, right? whole cube, volume of a cube is a cubed, but then there's two, Jesus Christ, atoms per unit cell. Like a per cube is what I mean. Like two lattice points per unit cell, because we have the one in the middle. Another way you can see this is we could literally just do the dot product. So this volume is equal to, I'll take the 1/2 a cubed out from here, right? And you'll see why. And I have -1, 1, 1, 1, -1, 1, 1, 1, -1. And you just take the determinant of this. And this right here should come out to 1, and then we get the a cubed over 2. Right? Because in each one I have an a and a 1/2, and I take it out per row. And that's how matrices work. Okay, so then we get this expression that b1 is 2 pi over a of y plus z hat. b2, Jesus, equals 2 pi over a x hat plus z hat. Shit, and then I'm dying right now, equals 2 pi over a x hat plus y hat. And these are all from the same expressions we saw before, this one right here. Where what you do is, like, for b2, it would be 2 pi a3 cross a1 over vc again, and so forth. It's kind of like the Levi-Civita symbol, like cyclic permutations. Okay, so it's kind of interesting, actually, that if we look at these right here, these vectors, these are actually just the primitive vectors of an FCC lattice. So in other words, an FCC lattice, this is important, is the reciprocal lattice of a BCC lattice. Kind of crazy. So the general reciprocal lattice vector is, I'm just going to screenshot this because I'm not writing all that. It's a lot. Is VB1 plus VB plus V2 B2 plus V3 B3, which you can take the 2 pi over A and then plug in our values for V2, V3, V1, and so forth. So now if we see, right, the primitive basis vectors of the FCC lattice, we see that they're actually the exact same as the reciprocal vectors of the BCC lattice. So, yes, nice. Okay, let me get some water, but take a second to digest that. Okay, so now what happens is we want to go from the reciprocal lattice to FCC lattice. Reciprocal lattice to FCC lattice. You can probably guess where this is going. So if we look at the primitive translation vectors of the FCC lattice, figure 14, hint, hint, the reciprocal vectors of the BCC, we get, oops, I scrolled too far. We get A1 is 1/2 A, Y hat plus Z hat. I like to write that instead as 0, 1, 1, but whatever. So A2 equals 1/2 A, 1, 0, 1. So we know which one we do when we do the matrix multiplication. And then A3 equals 1/2 A, 1, 1, 0. The reason why is we find the volume, right? That's 1/2 A cubed, like that. Integral of 0, 1, 1, 1, 0, 1, 1, 1, 0. Where if you want to do the math, you can. So this one goes to 0 because it starts with 0. So that equals 1, or I guess minus 1 times 0 minus 1, okay, plus 1 times 1 minus, so this minus 0, which is minus 1 plus 1, oh shit, plus 1 plus 1, which is 2. So we get 1 over 8 A cubed times 2, which is 1/4 A cubed. That's how you calculate the volume of it. And that's what they get here. Very nice. So then if we plug it into the reciprocal lattice vectors of, where B1 equals 2 pi A2 cross A3 over VC, we get 2 pi over A negative x hat plus y hat plus z hat. Oh, that looks very familiar. That was the BCC one. And then we get B2 equals 2 pi over A x hat minus y hat plus z hat. And then we get B3 equals 2 pi over A x hat plus y hat minus z hat. Okay. So the BCC lattice is the reciprocal to the FCC lattice. And the volume of the reciprocal lattice is 4 times 2 pi A cubed. So the shortest G's are the 8 vectors 2 pi over A plus or minus in all directions. So the boundaries of the central cell in the reciprocal lattice are determined for the most part by the 8 planes normal to these vectors at their midpoints. But the corners of the octahedron thus formed are cut by the planes that are perpendicular bisectors of 6 other reciprocal vectors. So let's note that 2 pi over A, 2x is a reciprocal lattice vector because it's equal to B2 plus B3, blah, blah, blah. So the first Brillouin zone, so again, the first Brillouin zone is the smallest bounded volume about the origin in the reciprocal space, and it's the truncated octahedron shown in figure 15. Here you go, the Brillouin zone of the FCC lattice. And we see that the reciprocal lattice is body-centered, right? And we just have all these planes, and we get 1, 2, 3, 4, 5, 6, 7, 8, so forth. Okay. Nice. So let's look at if Fourier analysis is the basis. So when we have the condition delta k equals g is satisfied, in other words, we intersect the plane. Imagine like this is our lattice, and we have k vectors that intersect the Wigner site cell or the Brillouin zone. We can write the scattering amplitude for a crystal of n cells can be written as f of g equals n integral over the cell over the whole volume, n of r, the electron density, e to the negative I g dot r, which is just n sg, where sg is this thing called the structure factor and is defined as an integral over a single cell with r equals 0 at one corner. Okay, so it's often useful to write the electron concentration, n of r, this right here, as a superposition of electron concentration functions and j associated with each atom j of the cell. So if rj is the vector to the center of the atom, then the function nj r minus rj defines the contribution of that atom to the electron concentration at r. Right? So the total electron concentration at r due to all atoms in a single cell is the sum. So n of r is equal to sum over j equals 1 to, I guess, however many there are, nj r minus rj, where there's s atoms in the basis. So the decomposition of n of r is not unique, so we cannot always say how much charge density is associated with each atom. It's not really an important difficulty. So we can rewrite the structure factor, this thing right here, minus the nr, Jesus, as integrals over the s atoms of the cell. So we can say s of g is equal to the sum over j, the integral over the cell, dv, nj r minus rj e to the I g dot r, negative I, sorry, dot r, which is going to equal sum over j e to the negative I g dot r, integral dv nj of rho e to the negative I g dot rho, where rho is defined as r minus rj. So we can define the atomic form factor f of j as the integral dv nj rho e to the negative I g dot rho. Okay, integrated over all space. So if nj of rho is an atomic property, fj is an atomic property, right? Because you see how they're related. Okay, so if you combine 41 and 42, 41 and 42, to obtain the structure factor of the basis in this form, we can say the structure factor is the sum over j, f of j, the atomic form factor, e to the negative ig dot rj. So the usual form of this result, falls on writing for atoms j. So we can say R of j, right, is xj, A1, plus yj, A2. Because remember, this is just a vector to a single atom from some origin. Oops. A2 plus zj, A3. So therefore, the reflection G dot Rj is just V1, B1 plus V2, B2. So our G vector plus V3, B3 dotted with Xj, A1 plus Yj, A2 plus Zj, A3. And of course, only these terms survive because of the rules. So 2 pi V1 Xj plus V2 Yj plus V3 Zj. So therefore, we can write the structure factor in terms of V1, V2, V3 as the sum over j of f of j e to the negative I 2 pi V1 Xj plus V2 Yj plus V3 Zj. In other words, the structure factor, so the structure factor S does not need to be real because the scattered intensity, right, is S dot S, or I guess it's the inner product. So S times the complex conjugate of S. So that's S times S is real. Okay, that was a lot of stuff, but let's see that in action after I take a sip of water. Cool. Okay. So the BCC basis referred to the cubic cell has identical atoms at x equals 1, y equals 1, and z equals 0. So let's look at the structure factor of the BCC lattice. So we can write the structure factor of V1, V2, V3 is equal to F1 plus E to the minus I pi V1 plus V2 plus V3. So I plugged in for x1 equals y1 and z1 equals 0. So x2 equals y2 and z2 equals 1/2. So the value of s is 0 whenever the exponential has the value negative 1. Right? So if this value has the value negative 1, then f goes to 0, so s is 0. Right? Okay. So s equals 0 when v1 plus v2 plus v3 odd integer, right? So if I have, I don't know, 3 odd, like let's say they're all odd. So I have 3 plus 5 plus 7, that's 10, 15, 15, e to the negative I 15 pi is negative 1 on the complex plane. So we just get negative 1 for this exponential here, and we get 0 for the structure factor. However, s equals 2f whenever v1 plus v2 plus v3 are even integers, because remember v1, v2, and v3 are all integers regardless. So if I have like 3 plus 5 plus 2, something like that, that's an even integer because I get a 2 pi there. This goes to 0, so I get this goes to positive 1, so then I get a 1 plus 1 is 2. Okay. So metallic sodium has a BCC structure. So the diffraction pattern does not contain lines such as 100, 300, 111, or 221, right? Because if I add them up here, I get odd integers. But it does have stuff such as 200, 110, and 222 are always going to be present because they always add as even integers. Okay? So let's think what the physical interpretation of the result of the 100 reflection vanishes. So the 100 reflection normally occurs when reflections from the planes that bound the cubic cell differ in phase by 2 pi. However, in the BCC lattice, there is an intervening plane of atoms labeled the second plane in the figure, which is equal in scattering power to the other planes. So situated midway between them, it gives a reflection retarded in phase by pi with respect to the first plane, which thereby canceling the contribution from that plane. You have destructive interference. So the cancellation of the 100 reflection occurs in the BCC lattice because the planes are identical in composition. And a similar cancellation we can find in the HCP. So let's look at figure 16 real quick. Figure 16. Okay. So here we see we have a phase difference of pi, so they get canceled out. So we have the 1, 0, 0 reflection from a body-centered cubic. The phase difference in successive planes is pi, so the reflected amplitude from two adjacent planes, right, is going to be pi, so we get a contribution of 0 between the two. So these two screw each other over, basically. Okay. All right. So if we look at the structure factor now of the BCC plane, of the FCC lattice, sorry, we have identical atoms at 0, 0, 0, 0, 1, 2, 1, 2, 1 half, 0, 1 half, 1 half, 1 half, 0. So we can rewrite 46, S of V1, V2, V3 as f of 1 plus e to the negative I pi, V2 plus V3 plus e to the negative I pi, V1 plus V3 plus e to the negative I pi, V1 plus V2. Okay. So then, if we have all even integers, so all even, S is going to be 4f, right? All of these are even, so we have an answer that's even over here. So e to the even number times e to the negative I pi times even number. It's going to give us a 1. So we get a 1 here, a 1 here, and a 1 here. So we get S equals 4f. However, if only one of the integers is odd, right? So if only one of the integers is odd, so we get, so 2 of the 3 will be odd. So we'll say V1 equals 1, V2 equals 2, V3 equals 2. V2 plus V3, this right here is even. This one right here is odd, and this one right here is odd. So we get a -1, a -1, a +1, and a +1, so we get 0. So if 1 odd, S equals 0f. And then the same argument applies for other stuff as well. So therefore, in the FCC lattice, no reflections can occur if any of the indices are partly even or partly odd. You either need to have them all odd or all even, right? Because if they're all odd, then we have two odds make an even, so each sum is even. Okay. So if we look at figure 17, both KCL and KBR have an FCC lattice. So let's look at figure 17. What we see, right, is we don't see anything that's has even in odds, right? They're all either all odd or all even. All the reflection peaks. Okay. Now we can talk about the atomic form factor. So in expression 46 for the structure factor, we had this quantity Fj, right, which is a measure of the scattering power of the jth atom in the unit cell. So the value of F involves the number and distribution of atomic electrons and the wavelength and angle and scattering of the radiation. So let's give a classical calculation for the scattering factor. So the scattered radiation from a single atom takes account of interference effects on the atom. So we can define the form factor in 42. So f of j as the integral over dv of nj of r e to the negative I g dot r, with the integrand extended over the electron concentration associated with a single atom. Let's let r make an angle alpha with g such that g dot r is gr cosine alpha. If the electron distribution is spherically symmetric about the origin, right, then we have f of j equals 2 pi integral dr r squared d cosine alpha nj of r e to the negative I gr cosine alpha, which is just 2 pi integral dr r squared nj of r dot e I gr minus e negative I gr over I gr. Okay, and after integration over d cosine theta between -1 and 1, the form factor is then given by f of j equals 4 pi integral over dr r squared nj of r sine gr over gr. Okay, so that tells us then if the same electron total density were concentrated at r equals 0, only gr equals 0 would contribute to the integrand. So in the limit that sine of gr over gr, sorry, this equals sine of gr over gr, in that limit, f of j equals 4 pi dr njr r squared which is Z, the total number of electrons, of atomic electrons. That's if sine of GR over GR goes to 1. Okay. So the overall electron distribution of solid as seen in XRD is fairly close to the appropriate free electrons. So the statement does not mean that the outermost or valence electrons are not redistributed somewhat in forming the solid. It only means that X-ray reflection intensities are represented well by the free atom values of the form factors and are not very sensitive to small redistributions of the electrons. So that was a lot of words. Let's quickly summarize what we went over today. So the Bragg condition can be stated as simply 2D sine theta equals n lambda, delta k equals g, or 2k dot g equals g squared. Now the Laue conditions are that a1 dot delta k equals 2 pi v1, a2 dot delta k equals 2 pi v2, and a3 dot delta k equals 2 pi v3. So each one represents a cone of intersection. Okay, and the primitive translation vectors of the reciprocal lattice are given as shown. I think I wrote them down enough. And the reciprocal lattice has the form v1 b1 plus v2 b2 plus v3 b3. You might see it instead written as g equals hkl. So hb1 plus kb2 plus lb3 means the same thing. So the scattered amplitude in the direction k prime equals k plus delta k equals k plus g is proportional to the geometric structure factor given over here, which is the exponential of the dot product between rj and g, which is just the multiplying the coefficients together of their respective directions. Okay. Any function invariant under a lattice transformation T may be expanded in a Fourier series of the form classic Fourier series. And the first Brillouin zone is the Wigner-Seitz primitive cell of the reciprocal lattice. And only waves whose wave vector k drawn from the origin and terminates on a surface of the Brillouin zone can be diffracted by the crystal. So crystal lattice, the first Brillouin zone of a simple cubic, is going to be a cube. The body-centered cubic is going to be a rhombic dodecahedron, and the face-centered cubic is going to be a truncated octahedron. Okay, that's all I have for today. Hopefully the stitching of this video doesn't go too poorly, and I hope you guys learned something today. And I guess without further ado, I will see you guys next time. See ya.